So good afternoon. You are welcome to the fifth weeks of the facilitation for this course. Last week, we stopped at the discussion about ferromagnetism. We laid the foundation of the concept behind ferromagnetism, and we moved to the point of defining what ferromagnetism is, the examples, and also we concluded by looking at Coriolan's law. So which describe the observed susceptibility relation in paramagnetic region above the Curie point. So we continue from that place today and see how far you can go by trying to extend our discussion to antiferromagnetism today. So let us now determine the value of the main field constant lambda. An atom with angular momentum quantum number J has 2J plus 1, which is equally spaced in energy levels in the magnetic field. Therefore, the magnetization, we can write it as M is equals to Nj G Ng G mu B Bjx, where X in this case is G J mu Hk H divided by Kt. So the Brillouin function Bj is given by this expression, which is 2.19. So now, if X is far less than 1, then we can compute the susceptibility to be this. So where the effective numbers of Bohr magneton is defined by this, P. So the value of Wen's field constant can be determined as follows. So we can use this relationship to determine the values of the Wen's constant. So where X in this case, in this expression 2.222, is the spin angular momentum quantum number. Now let's look at spontaneous magnetization. In the case of spontaneous magnetization of ferromagnetic substance is said to have a spontaneous magnetic moment if it possesses a magnetic moment, that is, even in the absence of applied magnetic field. That if we don't have an applied magnetic field in the materials that has ferromagnetic properties, then you're supposed to have a spontaneous magnetic moment when this thing is not present. So in order to calculate the spontaneous magnetization as a function of temperature, we can use equation 2.18, so which is like this. Then in the absence of applied magnetic field, that is when magnetic field is not present, then you have this X G mu lambda ms over kt. So meaning that Bx is not there, which is the magnetic field. So please note that at a temperature far less than the Curie temperature, ms we obtain ms by multiplying ms by plotting ms versus s as given in equation 23. That is, when you plot the graph of magnetization against x, the distance now, you get your ms. So the domain theory of ferromagnetism, every piece of ferromagnetic material does not have a strong magnetic field, despite the fact that all the spins are aligned. That is, all the spins in ferromagnetism align in the same direction, but they don't have a strong magnetic field. So iron and other ferromagnets are often found in an unmagnetized state. At temperature well below the Curie point, the electronic magnetic moments of ferromagnetic specimens are essentially all lined up. That is, every one of them will be up. So when this is just the stories discussed by Wen and all these things. Now, let's look at the Bloch wall. The term Bloch wall denotes the transition layer which separates adjacent domain magnetized in different directions. The essential idea of the Bloch wall is that the entire change in spin direction between domain magnetized in different directions occurs in a gradual way over many atomic planes. So what I'm trying to say is that if you look at the directions, since they have different effects at different points, the way they move is different. You will see it here now. Look at this picture. So look at them. Some of them are pointing towards this direction, while some are pointing towards the north direction. And you can see how they go. So this is a kind of Bloch wall separation domain concept. So the total exchange energy of the lines of n plus 1 atom is thus, so this is the energy, Since the exchange energy of a wall is inversely proportional to the thickness, the wall might spread out until it filled a sizable proportion of the crystal, where it's not for the restraining effect of the anisotropic energy, which acts to limit the width of the transition layer. So we now consider a wall parallel to the cube face of a simple cubic lattice, separating domains magnetized in opposite direction. The energy per unit surface area may be represented to a good approximation as the sum of the computation from exchange and anisotropic energy, which is this. So the exchange energy is given by equation 2.27. So each atoms through the wall normal to the plane of the wall, there are 1 over a square such lines per unit area, where a is the lattice constant. So you have this expression. So the anisotropic energy is this. So then the domain dimension. So if we consider the domain width as shown in figure 2.3, the energy can be written as this, as shown in equation 2.34. So the volume contained within the domain of the closure is oriented in the direction of hard magnetization and involves an energy K per unit volume, where K is an isotopic constant. Per unit area of crystal surface on one side, the volume of the domain, which is given as equation 2.35. So now, if we put them together, we can compute the total energy per unit area to be equation 2.36. So also, we go down like that, it's just a kind of uh, mathematical expression to express some of the terms that, or some of the functions that exist in ferromagnetism. Now let's look at antiferromagnetism now. So in the case of ferromagnetism, we say all the spin are lying in one direction, but in this case, they are lying in opposite direction to each other. So technically speaking, their magnetic moment will be zero because they are in opposite direction. So the special origin of the Wenz field is in the quantum mechanical exchange integral. It can be shown that the energy of interaction of atoms I and J bearing spin x1, Si, and Sj contains a term, this, as exchange interaction, where J is the exchange integral and is related to the overlap of the charge distribution I and J. So when the exchange integer J in equation 240 is positive, we have ferromagnetism. When J is negative, we have antiferromagnetism. So in material that exhibit antiferromagnetism, the magnetic moment of atom are molecularly related to the spin of electron, align in a regular pattern with neighboring spin pointing in opposite direction as shown below. So you see that some are up, some are down, some are up, some are down. These are the arrangement of antiferromagnetism in the material. So now, your self-assessment exercise are differentiate between ferromagnetism and antiferromagnetism. Then you have to explain ferromagnetism in terms of the exchange integral J. These have been discussed up. So now let's look at ferrite. Ferrite of magnetic interest. Ferrite of magnetic interest belong to the group of compounds represented by the chemical formula this, where M is divalent metal ion, that's this, or mixture of the ion. So also we look at magnetic resonance. So the question we should ask ourselves is that what do we mean by magnetic resonance, and what are the importance of this? On daily basis, all these things are being used around our vicinity in the laboratories and in the schools, but we don't really know that the concept behind this. So what are they used for? They are used for the electronic structure of single defect, which help us to reveal the structure of the absorption. We can also use to look at the motion or spin of the surrounding and the line's width, which can give us the line width, and the internal magnetic field sampled by the spin. So then also we have nuclear magnetic resonance. So nuclear magnetic resonance, that is NMR. It's a physical phenomenon in which magnetic nuclei in a magnetic field absorb and re-emit electromagnetic radiation. So this energy is at a specific resonance frequency, which depend on the strength of the magnetic field and the magnetic properties of the isotope of the atoms. So in practical applications, so we see them in the frequency is similar to UHF and VHF television broadcast, that is from 60 to 1000 megahertz. So NMR allows the observation of specific quantum mechanical magnetic properties of the atomic nucleus. So many scientific techniques explore NMR phenomena to study molecular physics, crystals, and non-crystalline materials through NMR spectroscopy. So NMR is also routinely used in advanced medical imaging techniques such as magnetic resonance imaging. So all isotopes that contain an odd numbers of proton or neutron have an intrinsic magnetic moment and angular momentum. In other words, a non-zero spin, while all nuclides with even number of both have a total spin of zero. The most commonly studied nuclei are hydrogen and carbon. So we have many of them. You can see them as listed here. So a key feature of NMR is that the resonance frequency of a particular substance is directly proportional to the strength of the applied magnetic field. It is this feature that is exploited in imaging techniques. If a sample is placed in a non-uniform magnetic field, then the resonance frequencies of the sample nuclei depends on where the field they are located. Since the resolution of the imaging technique depends on the magnitude of magnetic field gradient, many efforts are made to develop increased field strength, often using superconductors. Though the effectiveness of NMR can also be improved using hyperpolarization or using two-dimensional, three-dimensional, and higher dimensional multiple frequency techniques. So now, the principle of NMR usually involves two sequential step. The alignment of the magnetic nuclear spin in an applied constant magnetic field H naught. Two, the perturbation of this alignment of the nuclear spin by employing an electromagnetic, usually radio frequencies, pulse. The required perturbing frequency is dependent upon the static magnetic field and the nuclear observation. So two fields are usually chosen to be perpendicular to each other as this maximizes the NMR signal strength. The resulting response by total magnetic spin is the phenomenon that is exploited in NMR spectroscopy and magnetic resonance imaging. Both use intense applied magnetic field in order to achieve the sparse and high stability delivered. So this is just the basic idea or the concept behind NMR. So now let's look at ferromagnetic resonance. They are more or less like NMR. They also do the same thing. We also have antiferromagnetic resonance, so which are similar in. So I think uh, with this now, we technically come to the end of the classes on ferromagnetism and antiferromagnetism. So if you have any question you are free to ask, you can try and look at some of the uh, tutors assignments and see how you can go about them. If you have any issue, you can actually get back to me and ask your questions. So by next week, we start discussion on imperfections in solids. So any questions? Any questions? Okay, there is no questions. I think we have to stop the lecture for today.